Welcome back. In this set of lessons, we're looking at medicinal chemistry. When you're a child, you might have heard of the story, The Wind in the Willows. You might have read that. Well, willows are a type of tree. They're not indigenous to Australia. They're, I think, an English tree, but they've got many uses, including making cricket bats out of the wood. But also the willow bark contains a compound called salicin, which is related to salicylic acid that is a reactant used to make the pain-relieving medication aspirin. So willow bark contains salicin, which is very close in structure to salicylic acid and the painkiller aspirin. We'll talk more about that in this lesson. Okay, so this lesson we're going to look at the extraction, the purification and the identification of medicinal molecules. So the study design dot points relate to solvent extraction and distillation of natural plant compounds, a bit of a description about medicinal organic molecules themselves, and a discussion about chirality. If we go back and have a look at the willow tree, this is just one of thousands of plant molecules that have healing properties. So aspirin is well known for reducing pain, for reducing fever, and also for thinning blood. And the willow tree, the willow bark, contains this compound. It contains lots of compounds, but this particular structure that we've got here is salicin from willow bark. And it can be converted to salicylic acid, which is the starting material for making the painkiller aspirin. So the medicinal molecules we're going to look at are compounds that have healing properties. Not all properties have healing properties. Some molecules are toxic, but in this case for a medicine, they must have some beneficial property about them. So first of all, to get the plant compounds out of the willow bark or the other plant material, we need to extract the compounds using a solvent. And remember, a solvent is a substance that can dissolve solutes into it. So to extract and separate natural plant compounds, because plants are mixtures of compounds, it's important to choose an appropriate solvent for that particular compound. So polar solvents include water and ethanol. Solvents with limited polarity include acetone and dichloromethane. And non-polar solvents include hexane, ether and chloroform. So it depends on the substance that needs to be extracted, how we would choose an appropriate solvent. In the solvent extraction process, which we've shown on the right, then we put the mixture into a separating funnel. So that's this piece of glassware here, a separating funnel. Just like a burette has a tap, a separating funnel has a tap. So we've got the mixture in the separating funnel. Then we add a solvent. So if we're starting off with a non-polar solvent here, we might add a polar solvent to it as well. Then we start getting separation of the compounds. And the red molecules are moving up because they're polar, they're moving into the polar phase, and then the non-polar phase can be separated off. Although you see occasionally you get a polar impurity coming through. And we close the tap when we've separated that layer, the basic mechanism of solvent extraction. So the liquid with the higher density or greater density will be down the bottom, and that will be extracted first. And sometimes these could be in multiple layers. So if we have layers, it means the layers are immiscible. They haven't bonded to each other. They haven't mixed properly. So it's a set of liquids that don't mix together. So these two layers are immiscible. So while solvent extraction is useful, it does have some limitations. It's a slow process that requires large volumes of solvent, and that can be an issue when we're talking about green chemistry, just the quantities of chemicals that are used. And it can be ineffective at removing impurities that have similar solubility as the target molecules. So in this case, this red molecule has similar characteristics to the chosen material. So one of those red molecules has made it through into this beaker. Another technique that's used is distillation. This is a simple distillation apparatus that we've got here, and it's useful when there's two liquids with significantly different boiling points. And an example would be ethanol and water. So we've got the mixture in this flask here. We've got boiling chips to make sure that it doesn't splutter when it's heating. The vapours move up, and the vapour with the lower boiling point comes out first. And we've got a water jacket around in this condenser, flowing water that's cold. And so the vapour that comes down condenses into a liquid that is the distillate that comes through at the end of the condenser. It's capped so that no vapours can escape, so they just keep condensing back into the boiling flask. And there's a thermometer so we can see at what temperature the various liquids are vaporised. So ethanol, for example, has a lower boiling point than water. It boils at 78 degrees Celsius, whereas we know that water boils at 100 degrees Celsius at sea level. In this case, we've got a Bunsen burner here, but we would actually be using a heating mantle if we were actually heating ethanol, because ethanol is flammable. So we would use a heating mantle instead of a Bunsen burner to avoid explosion. And this process can be repeated several times to remove the substance with the lower boiling point. So this is the lower boiling point. So what we're left with in the boiling flask is the higher boiling point liquid, and in the distillate flask, the lower boiling point. So we've separated them. So the simple distillation is a method of separating compounds based on a difference in their boiling points by continual evaporation and recondensation in this closed flask. And anti-bumping granules or boiling chips are added to the distillation mixture to distribute heat and avoid explosion and sputtering of the mixture. Another technique that can be used is using steam distillation apparatus. So this is a diagram of steam distillation apparatus, and it's useful for substances with high boiling points such as oils. In the process, water vapour, so we've got water here, is pumped through the distillation apparatus, which reduces the vaporisation temperatures of the substance in the mixture, and then the steam is fed into the mixture to be distilled, and the steam distillation minimises heat destruction of compounds. Then the compound to be extracted comes into the condenser tube, condenses from a gas into a liquid, and the distilled liquid can be extracted, preserving the desired product. So it's a technique that's using injection of water vapour to lower the boiling point of substances and minimise decomposition. Okay, let's look at some more medicinal compounds now. So many medicinal organic compounds are large molecules, not all of them, but many are large, and many contain ring structures and polar groups. So if we look here, we've got benzene rings, we've got another ring here, and we've got some polar groups. So an example is the emu bush. This is an Australian plant, the emu bush. One of its compounds that it contains is pinobanxin, and it's one active ingredient or medicinal compound in the emu bush. So an active ingredient is a substance that produces a chemical or biological effect and therefore has useful medicinal properties. Okay, we can use HPLC and spectroscopy that we've already looked at to identify medicinal organic compounds and to separate them. So we can use HPLC to separate the compounds, and mass spectrometry, 13 carbon NMR, 1 hydrogen proton NMR, to determine the structure of these medicinal compounds. So any plant contains hundreds and thousands of different compounds. Are useful, some of them aren't. In the emu bush, there are numerous useful medicinal compounds. So there's more than just one. And we can use HPLC to separate the compounds. And here's a few examples. So we've got the pinobanxin 3 acetate, the pinobanxin 3 cinnamate, and this other compound here, which I'm not even going to try and pronounce. And these are all examples of substances that are in the emu bush. Let's look at a worked example. So in emu bush, it contains many active ingredients extracted using HPLC and then further analysed. Identify the peaks of the 3 compounds present in emu bush extract, which is the dark orange line, that are worth exploring for their medicinal benefits. Now, the peaks that we're looking at are the tested potential compounds, and they're in light orange. So we want to see where the dark orange and light orange chromatograms overlap. So we've got peak 1, peak 2, and peak 6. So that's the answer to A. Then part B says, identify the peaks of a compound present in emu bush, which is the dark orange, that has unknown medicinal potential. So the known medicinal potential are the light orange peaks. So 4, 5, and 7 and 8 are known. For the unknown, we're going to look at peak 3 because that's the one that we don't know anything about. Now we're going to talk about chirality. Chirality is a really important concept to do with structure of compounds, particularly in the biological context. So hands are chiral. Chiral objects can't be superimposed. They can be reflected in a mirror, but they can't be superimposed. So I could put a mirror between my thumbs and my second finger, etc., and I see a mirror image, but they can't be superimposed because my thumb and my pinky fingers are in the way of each other. So those objects are called chiral. Achiral means A means the opposite. So it's a compound with a superimposable mirror image. So its mirror image can be superimposed on top of itself. It has a plane of symmetry. For example, this bottle, if we divide it in half vertically, then its mirror image can be superimposed onto it. So it's an achiral object. So achiral compounds can be superimposed on each other when reflected in a mirror. Chiral compounds can't be superimposed. And you might ask why we're talking about hands and feet and bottles. And that's a good question. Because we want to talk about chirality with compounds now. A chiral compound, when reflected in a mirror, cannot be superimposed. So to talk about a chiral compound, we need to define what that is. It has a non-superimposable mirror image, but it's a compound that contains a chiral centre, which is a carbon that contains 4 different atoms or groups of atoms bonded to it. So here, with our skeletal structure, we're implying that we've got a carbon that sits in the middle, and then we have a hydrogen, that's 1 atom bonded. We have a fluorine, so that's a second group of atoms bonded. Then a bromine, so that's 3, and then chlorine is 4. So there's 4 different atoms or groups of atoms bonded. And sometimes we represent a chiral carbon with an asterisk. So we've got this asterisk here. Now, if we look at this compound next to a mirror, we can see the fluorines are mirror images of each other, and the chlorines, the bromines are further apart, and the hydrogens. But if we rotate it 180 degrees like we do our hand, it can't be superimposed. Not all of the atoms will line up. So that means that this compound is a chiral compound, and it has at least 1 chiral centre, which is a carbon with 4 different atoms or groups of atoms bonded to it. Did you know that any atom with a double or triple bond coming from it, including aromatic rings like benzene, cannot be a chiral centre? So a carbon, in order for it to be chiral, must have 4 different atoms or groups of atoms bonded to it, which we call 4 unique chemical environments. Okay, a chiral compound, when reflected in a mirror, we've just said cannot be superimposed. So there's a flow chart here that you can actually use to determine if a molecule is chiral. Has the molecule got a chiral centre? That means a carbon with 4 different atoms or groups of atoms. If the answer is no, then the compound is not chiral. If the answer is yes, it contains one chiral centre. If it has more than one chiral centre, yes. Does it have a plane of symmetry? If yes, then it's an achiral compound, so that plane of symmetry will cancel out the chirality. But if we have one chiral centre only, then the compound will be chiral. Or if we have more than one chiral centre that hasn't got a plane of symmetry, then it will be a chiral compound. When we're talking about chirality, if we've got two chiral compounds, they're also called enantiomers or two optical isomers. And you might wonder why we call isomers optical. Optical isomers rotate polarised light in one particular direction. They can either rotate it to the left or to the right. And a racemate is an approximately 50-50 mixture of a chiral compound's two optical isomers or enantiomers, which does not rotate polarised light in a specific direction. So a racemate is a mixture of two optical isomers in approximately equal quantities. Okay, so we've got one molecule rotating one way, another molecule rotating the other way, and they cancel each other out. So racemates don't rotate polarised light. Racemates are named after racemic acid, which is a mixture of left and right-handed tartaric acids, which is an organic acid, discovered by famous scientist Louis Pasteur. Now, optical isomers or enantiomers have similar physical properties, such as melting point and boiling point, but they may have very different biological activity, and this becomes vital when we're talking about medicinal compounds. Receptors on cells have specific three-dimensional shapes. And if we have a look at the drawing that we've got here, we've got a circle shape, a square shape, and a triangle shape, and that corresponds to the different groups of atoms attached to this particular carbon. So this is a chiral carbon. But if we have the mirror image, the optical isomer or enantiomer, then the triangle doesn't fit in the circle. The square will fit in the square, but the circle won't fit in the triangle. So only one optical isomer or enantiomer will fit a biological molecule or cell quite often. A very sad example was the case of thalidomide. It was a medicine that was prescribed many years ago as a cure or a treatment for morning sickness in early pregnancy. And the only differences between these optical isomers or enantiomers is the way that this nitrogen is bonded here. In one way it's pointing out and the other way it's pointing in. And that's the only difference in between these two optical isomers. The R form is actually a cancer treatment, so has some use. But the S form, this caused birth defects, serious birth defects. And unfortunately, sometimes you can have conversion from one isomer to another optical isomer called chiral inversion, and the body can actually convert the cancer treatment into this serious defect version. Okay, so let's summarise what we've learnt. Medicinal molecules can be extracted from plants using solvent extraction, simple distillation and steam distillation. Plant materials can be analysed using HPLC, IR spectroscopy, mass spectrometry, 13 carbon and 1 proton NMR. Chiral compounds contain at least one chiral carbon, which means attached to 4 unique chemical environments. Sometimes they're symbolised as an asterisk, or you might be asked to label them as that. They also lack a plane of symmetry. Racemates are approximately equal mixtures of optical isomers, and the other word for optical isomers is enantiomers. And some medicinal compounds are specific optical isomers that attach to specific three-dimensional receptors on cells. What's coming next? Enzymes and medicines. So see you soon.